Quantum mechanical model. According to this model, electrons do not orbit the nucleus, but occupy space around nucleus called orbitals. An orbital is defined as a region in space around a nucleus in which the probability of finding an electron is high. An orbital is also called an electron cloud. In example 1, both 1s and 2s orbitals have the same shape as they both are s orbitals. However, because the principal quantum number is different, 1 for 1s, 2 for 2s, the size of orbital is larger for 2s compared to 1s. In addition, 2s orbitals have higher energy compared to 1s orbital due to the difference in principal quantum number. In example 2, s, p, and d orbitals have different shapes. In example 3, px, py, and pz orbitals have same shapes but differ in spatial orientation, or in other words, how the orbitals are aligned with the x, y, and z axes. Quantum numbers. Quantum numbers specify the properties of atomic orbitals and their electrons. Each electron in an atom has a set of 4 quantum numbers, which are principal quantum number, angular momentum quantum number, magnetic quantum number, and electron spin quantum number. Principal quantum number n specifies the shell of an electron. The combination between principal quantum number n and azimuthal quantum number L specifies subshell. Combination of principal quantum number n, azimuthal quantum number L, and magnetic quantum number M specifies the orbital which will be occupied by the electrons. The 4 quantum numbers describes an electron in terms of energy and its probable location, much like an address of someone living in an apartment building. If we have the address, we can find out where this particular person can be located. In the same way, if we have the 4 quantum numbers of an electron, we can also determine the most probable location of the electron around an atom. Principal quantum number n indicates the main energy levels of orbitals. It can have values of 1, 2, 3, 4 or any other integers. N is also referred as electron shell, where n equals 1 is the lowest energy level and the nearest to the nucleus. As n increases, the distance between the nucleus and the electron increases, and the energy level of the electron also increases. Maximum number of electrons in a shell can be given by the formula 2 times n squared. To further explain the principal quantum number, let's look at this example of the atom sulfur. Sulfur has 3 shells. Shell number 1 has 2 electrons. Shell number 2 has 8 electrons. Shell number 3 has 6 electrons. So the first shell is represented by the principal quantum number 1. Shell number 2, principal quantum number 2. And shell number 3, principal quantum number 3. Angular momentum quantum number L, also known as subsidiary, azimuthal or orbital quantum number. It specifies the shape of an orbital. It also divides the shell into smaller groups of orbitals called subshells or sublevels. The allowed value of L starts from 0, 1, 2 until the maximum value, which is 1 below the principal quantum number. If the L value is 0, the subshell is called S. If 1, the subshell is P, 2 is D, and 3 is F. Magnetic quantum number describes the orientation of orbitals in space, or also known as spatial orientation of orbitals. Based on the permitted value, we can determine the possible values of M. For example, if L is 0, there can only be one permitted value for M. If L is 2, the possible value for M can be any number between -2, -1, 0, 1, and 2. An orbital can hold up to 2 electrons. Magnetic quantum number divides subshells into individual orbitals. Magnetic quantum number and orbitals. This table shows the value of L, its respective orbital shape, possible values of M, number of M values, and number of orbitals in the subshell. S orbitals have spherical shape. L value is 0, its M value is also 0, and there is only one possible value for M. P orbitals have dumbbell shape, which looks like two spheres with an axis going through it. It has 3 possible values, which is -1, 0, and 1, and these values can be associated with three orbitals, px, pz, and py. D orbitals have complex shape. It has 5 possible values of magnetic quantum numbers, which can be associated with 5 different types of orbitals. This table shows the summary of relationship between N, L, and M. It also shows the number of orbitals related to a subshell and number of electrons related to the subshell, and also number of electrons per shell. Electron spin quantum number. Only 2 electrons can occupy any one orbital. The spin quantum number represents the rotation of an electron on its own axis, which can either be clockwise or anti-clockwise. There are 2 possible values of S, which is positive half and negative